Hello everyone, I'm Euicheol Lim, in charge of the processing memory architecture and CXL memory controller project in SK hynix. First of all, I'd like to thank you very much for inviting me to give this kind of keynote on computing and memory architecture and systems at this ISMM24. Actually, today I'd like to talk about the next generation memory solution as well as HBM, well known as AI memory for AI computing system. Actually, I'll focus more on the combining computing and memory system to provide higher performance and lower power consumption for AI services. Anyway, actually, it's 1:43, which means it's most sleepy time in whole day after lunch. So actually, I'll try to do my best to keep you awake until the end of this talk. This talk consists of 6 parts. First, I would like to introduce AI service and its algorithm trends and their impact on computer architecture. And I will briefly talk about the HBM, known as AI memory these days. And in the third chapter, we are going to cover the ChatGPT service, which has renewed that horizon of AI services and AI model, and the limitation of the GPU computing architecture for that service. After that, I will introduce that most energy efficient LLM accelerator solution using AiM, which is that SK hynix's first processing memory device. And as you will see later, those kind of AiM solution can overcome the performance and power issues of current AI computing system. In the next chapter, I will give an example of a general AI service and explain the whole kind of entire data pipeline. And lastly, I will introduce various specialty memory solutions, such as a CXL memory-based computational memory solution and the system architecture that I consider to be the ultimate goal. So let's get started. Before talking about the computing system architecture for AI, then we must first understand the trends of AI services and algorithms that become the workload for AI computing. So as a representative AI services, there are recommendation and natural language processing and vision processing system, as you will know. The recommendation system is composed of MLP and embedding that maps products or users in the real world to the deep learning world. And vision processing is built with around that CNN algorithm. Maybe you're most familiar with that. And for the natural language processing, the existing RNN and LSTM-based algorithm has been replaced with that transformer series now. So, yes, there were various algorithms for each services, as you see. But now, transformer algorithm is becoming mainstream model in all AI services. So I will introduce it again later, but in the end, I think the AI model direction will be the combination of that, just the embedding and the transformer, as shown in the picture on the right. So then now let's take a quick look at then why transformer has become a mainstream model in terms of algorithm and architectures. So as you know, then transformer became known through a paper titled "Attention is all you need," published by the Google in 2017. So transformer model ensures accuracy by leveraging self-attention to capture complex data dependencies, enabling precise learning of relationships on input sequences for superior performance in natural language processing tasks. And in architecture-wise, it's highly parallel architecture processes input elements simultaneously, so accelerating training on GPUs and enhancing scalabilities for efficient handling of those kind of large data sets. So to summarize briefly, transformer can provide higher accuracy by attention mechanism and can also provide higher performance and higher hardware utilization by maximum parallelism. That's why transformer became a superstar in AI model now. So then is AI service possible with just a transformer? In order for the AI model to work, then it is necessary to translate the real space data into the vector data that the transformer algorithm can understand. For example, when performing natural language processing, then words should be mapped. When performing the vision processing, then image pixel information should be translated. And in case of recommendation service, then product item and user information should be mapped to the deep learning space. So this kind of mapping operation is called embedding. So embedding requires a large capacity of memory to store the whole kind of mapping relation table and a high memory bandwidth to access the table as fast as possible. Therefore, embedding is a typical memory intensive function, Then after data in real space is transformed into the deep learning space through that kind of embedding, then a transformer model operates with this kind of transformed data. And as we'll be talking about later, transformer-based models vary depending on their size, whether they are computing bound or memory bound. Actually, the representative AI model with a higher proportion of embedding is that the recommendation service. On the other hand, both natural language processing or vision processing feature generally have a large proportion of a transformer model. So if you remember those kind of things, then it will be very helpful in understanding the appropriate workload for each memory-based solution, which will be introduced in the later chapter. So then now everyone will agree that the mainstream AI algorithm is that the transformer model. And one more trend we need to know is that rather than requiring different models for various services, then just one massive model performs various services with a high quality and various types of data, as like this. In addition, I'd like to discuss the trend of AI service level and AI model size. So as you can see the graph on the right, crazy large size transformer series models are emerging recently. So the model size is increasing exponentially, as you see. So as the model size grows to a certain extent, then it is possible to service various tasks that were not previously expected. So a good example would be ChatGPT, which was announced in end of 2022 and opened a new chapter for AI services. And the transformer-based larger model requires a higher performance computer and larger memory capacity. Fortunately, the transformer generative model such as a GPT series has a high ratio of memory intake functions, so it can be a good opportunity for a memory company like us. Then now I'd like to look at the researches related to the kind of power consumption caused by the movement of data. In terms of energy cost, we can see then how much energy is wasted by just the data movement on the left side on this slide. Looking at the result of 4 typical Google apps you can see that more than 60% of the power consumption is simply spent on data movement. And the graph on the right is a kind of roof-line graph of bandwidth and performance based on AI model characteristics. As you may know, then x-axis of a roof-line graph is that operational intensity, which is the ratio of the operation on the memory traffic. So as you can see, comparing with just a conventional workload, AI workload has very low operational intensity, which means overall performance largely depends on that memory bandwidth, not the process performance. Of course, there are lots of efforts to get higher computing element utilization by increasing number of batch and manipulating the processing algorithm. So applications, but still have a very lower operational intensity than conventional applications. So in order to, the low operational intensity the application has, then the more power consumed by data movement. So we need to make some kind of solution for those kind of application like AI services. As far as now, I introduced that AI model trends and reason why then transformer algorithm has become the center of AI model. And from now on, I'd like to talk about that just a high bandwidth memory, HBM, one of the most important components in the GPU system for AI processing now. Now, as you all know, then AI work require much larger memory capacity and higher memory bandwidth compared to other existing programs. And the GPU plus HBM system is more optimal than current previous CPU system for processing AI programs, such as the transformer-based model that are processed in maximum parallelism and require a large amount of data than conventional programs. So in particular, demand for HBM is rapidly increasing with that GPU boom following transformer algorithm which can utilize GPU well enough. And this is a brief introduction of a HBM solution. Actually, I briefly introduced HBM technology in terms of capacity, bandwidth, and power consumption. To increase that the memory capacity per unit area, then HBM memory comes in a stack of the memory dies that are vertically interconnected using TSV through silicon via technology. As can be seen from the name of the HBM itself, it provides exceptionally higher bandwidth compared to traditional memory technology. So this high bandwidth is achieved by using a wide interface up to 1,000 bits in a kind of HBM2 series. So, and HBM is designed to be more power efficient than conventional memory. So vertical stacking of memory dies reduce that distance that signals need to travel. So which helps to reduce the power consumption as well. So, and silicon interposer, you know that silicon interposer technology reduce that power for data movement between the HBM and GPU or CPU, like that. This slide shows that history and footprint of SK hynix's HBM. I'm not sure you know that, but SK hynix was the first to develop that HBM in 2014. After successful developing HBM for the first time in the world, and we are leading that HBM market and ecosystem through the continuous generation development. Actually, with each generation, we continue to increase HBM memory capacity and memory bandwidth while simultaneously reducing the energy consumption, which is very challenging task. Now, then, I'm going to briefly explain then each challenging requirement for the next generation HBM. First, we need to increase the memory capacity of HBM. One approach is to increase just a number of memory die stacked within a single HBM package. This requires advancements in TSV technologies, which allow for vertical stacking of memory dies, and additionally, improvements in the manufacturing process are necessary to enable the stacking of more memory dies within maintaining reliability and performance. And another avenue for increasing HBM memory capacity is to enhance the density of individual memory die. So overall advancements in packaging technology and TSV technology and memory die density are key for increasing the memory capacity of HBM. Second requirement is to just increase the memory bandwidth. So one way to boost memory bandwidth is to increase just the width of the memory interface, number of pins. So this involves using wider buses to transport data between memory and GPU, allowing for more data to be transmitted simultaneously. And wider bus needs advancements in TSV technology as well. And enhancement in I/O speed can improve the data transfer rate as well. But it may increase the power supply voltage and thus increasing the energy consumption, which we do not want. So anyway, this kind of increasing memory bandwidth is most difficult problem to solve in next generation HBM. And last requirement is to get higher energy efficiency. So in order to maintaining existing power while delivering a higher performance, then power improvement is required through the adoption of a logic process in HBM base die. So by introducing those kind of latest logic process to the HBM base die, we expect that power will be severely improved. Okay. Then do you think that if we use GPU and this kind of HBM solution explained so far, then will there be no problem with all AI services? I'm not sure. So to find out, let's discuss the ChatGPT service itself first. Actually, in general, for a new product to succeed in a real market, then it must possess all three of innovative technology and a stable investment and a wow factor. So AI chatbot such as ChatGPT is based on an innovative technology called, the large language model. And there is a strong investor and driving force such as hyperscalers like Microsoft. And many people are enthusiastic about the AI chatbot service now. So that's why AI chatbot is jumping over the chasm of moving from the early market dominated by early adopters to the mainstream market now. However, problem seems to exist with considerably higher operating cost and substantially longer service latency than previous services. So to resolve this, I'd like to propose a kind of AI-based accelerator system which can provide shorter service latency with a lower operating cost than the latest GPU system. Before presenting the solution, then I will explain the operation of AI chatbot inference and specifically which part has problems accelerating with the current GPU system. As shown in the figure, AI chatbot consists of a prompt stage that understands that input and the response stage that generates an answer. So I asked the question to AI chatbot. What are the issues of learning chatbot with GPUs? And he answers that there are several issues, including performance, cost, and power, blah, 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 when processing with GPU. So we may talk about his answer later, but here we will focus on just the AI chatbot inference working process itself. So during the prompt stage, then 9 words are processed in parallel. So 9 computing operations are performed just one time model parameter arrays. In this case, operational intensity, which is the number of operations per data read from the memory, is 9. So this is not the extremely memory intensive function. However, in the response stage, every time a word is generated, in case of 175 billion model, assuming 16-bit precision, then 350 gigabytes of data should be read from the memory every time. Just one computing operation is performed in one memory operation. Yes, in this case, operation intensity is just 1. It is an extremely memory intensive job. So performance depends on memory bandwidth. As you can see, it takes quite a long time to generate an answer. So actually, in this example, I used that just a word simply, but more precisely, basic processing unit of LLM is not the word, but the token. And on average, 1 token is around 0.75 words. So in this chatbot example, decoder shown 196 words, and its number token will be around 260 something. Then now let's quick calculate the minimum time required to process response stage with the latest GPU system. It's very simple math. Okay, in case of 175 billion model, then 5 GPU-A, in this case, GPU-A means H100 NVIDIA's. 5 GPU-A cards are required, and each GPU-A card can provide 3 terabytes per second of memory bandwidth, and giving a total of 15 terabytes per second of memory bandwidth. So the processing time per 1 token is dividing 350 gigabytes by dividing 15 terabytes per second, means that this processing per 1 token time is around 23 milliseconds. And whole impulse latency will be 6 seconds. So it's very simple math, and compared to existing service like a searching engine, this is very slow. So then why is so slow even when using the latest and expensive GPU system? As you can see on the right roofline graph here, GPU-A can provide 990 teraflops of performance. It's very huge computing performance capability. Actually, in case of that training, then since the batch size is large enough, you can fully utilize that GPU performance as shown on this graph. But in the case of response stage, with the operation intensity is 1, then only 3 teraflops, which is 0.3% of the GPU performance, can be utilized. So GPU is not efficient at processing just memory-intensive workloads, such as AI chatbot response stage. So you are paying high price of GPU, but only using 0.3% of performance, and thus wasting GPU power consumption. Of course, in order to better utilize that GPU performance, I know that there is lots of effort to increase the batch size during the LLM inference. However, you know that this is not an easy task, so as it affects the service latency directly. Therefore, there is a kind of need to create a higher performing and more cost-effective computing infrastructure than a current GPU plus HBM system. So then now I will introduce SK hynix unique LLM impulse acceleration solution now. Then why PIM? PIM means that processing in memory. I'd like to explain then why processing in memory technology can be an optimal large language model based LLM impulse accelerator. The figure on the left shows that the proportion of memory intensive processing time increases as that the AI model size increases. So as you can see that in the bot model, the proportion of memory intensive function is only 5%. But changing to the LLM such as GPT-2, it increases to 45%. And as the model size continues to increase, in the case of 175 billion model, it goes up to 92%. So the overall performance largely depends on just the memory bandwidth of the system. And one more interesting is that actually the memory intensive function we are talking about here is just one function, GEMV, matrix and vector multiplication. And the picture on the right shows that the concept of PIM, processing memory. PIM can utilize that the higher memory bandwidth inside the memory by operating processing unit on each memory bank in parallel. In addition, since only the result of a processing is just transmitted between XPU and memory, the data transmission between the XPU and memory is much reduced, improving energy efficiency as well. Actually, in our PIM device called AiM, we put a processing unit specialized in just the GEMV calculation, which is the most used in AI algorithm, as you can see the graph on the left. So due to those kinds of reasons, we believe that the AiM-based solution is suitable for LLM processing by providing higher memory bandwidth with less energy consumption. And please allow me to introduce then SK hynix's first PIM silicon product, AiM, which is GDDR6 memory-based PIM. Actually, from the beginning, AiM was created with a focus on just the GEMV operation, which is the most basic function of an AI model. So each AiM chip can provide 1 gigabyte of memory capacity and 0.5 terabyte per second of memory bandwidth, which is very huge when performing GEMV operation. And AiM support BF16 format precision. As shown on the upper left figure, each of the 16 banks has a MAC unit, so it can provide 16 times the bandwidth compared to the external bandwidth. So theoretically, its performance is up to 1 terabyte per second of memory bandwidth. However, since memory reading and GEMV operation constantly alternate, so the available bandwidth during GEMV operation is around 0.5 terabyte per second. Next, as shown on the right, I'd like to define then key performance metric for LLM-based AI services. Performance per memory capacity, TFLOPS per gigabyte. And also, since the operational intensity is 1 in a LLM response stage, it can be rewritten as just a memory bandwidth per memory capacity, terabyte per second per gigabyte. So if there is a target per token processing time, then it can be expressed as a reciprocal of a critical metric. So as can be seen on the graph on the left, right, then AiM can provide much shorter token processing time than the GPU-A. And actually, here I want to tell you one interesting story. Actually, we originally developed the AiM targeting for RNN and LSTM, which was very old one. At the time, the GenV portion was about 90% or more. However, after our development of AIM and as the transformer became the mainstream, the GenV portion fell below 10%, which was very disappointing. In other words, AIM specialized GenV function became useless in transformer, like a bird or something like that. Fortunately, with the release of GPT-2, the GenV portion rose to above 40%. However, even at that time, no matter how fast our AIM processed GenV, the overall performance improvement could not be doubled because there is still 60% processing time that AIM cannot improve. So, at the time, I asked my team members to find out which function would be good to add to AIM so that AIM could handle at least 60% of our processing time for LLM or something like that. However, after a few months, the team members came to the conclusion that AIM could handle around 90% of the total functions. So I was surprised and asked what they did. So they said that nothing was done and that it happened because just the model size increased. Actually, this is because that the layer that requires GenV grows squarely, while the other layers grows linearly. So therefore, as the model size increases in the future, then the improvement effect due to the AIM will increase as well, which is very good for us. And now I'd like to explain then how to deploy our AIM in the existing system. Perhaps even if you understand the benefit of AIM for LLM inference, maybe you may be hesitant to deploy it because you might think that in order to utilize AIM, then you need to modify the existing CPU or GPU and also change that software structure on top of it. However, as you can be seen in a previous chapter, as the LLM model size increases, then GenV operation takes up most of LLM processing so that AIM can alone accelerate LLM service without GPU or NPU or any kind of accelerator. So instead of replacing the memory in the existing accelerator with AIM, we suggest making on just the AIM accelerator card and plugging it into the AI server. Just a moment, please. Sorry. So actually, we call an AIM-based LLM accelerator card as just an AiMX card. So in this case, there is no need to modify the existing CPU, GPU, or accelerator, and software modification can be minimized. However, for the AiMX card, it is necessary to develop on this kind of AIM control hub that connects that server and AIM through that PCI and controls the AIM chips. And as will be explained later, we have already implemented those kind of reference design of this AIM control hub chip in FPGA. And this slide shows our AiMX architecture philosophy. As shown in the figure on the right, the AiMX card consists of an AIM control hub chip that receives job from the server and drive each AIM chips, and on AIM chips that stores just whole model data and processes GenV function very efficiently. And as you can see on the left, LLM consists of a GenV function which occupies most of the processing time, and various other functions which occupies a very small portion. And so AIM chip focus on processing just a fixed GenV function very efficiently, while the other various functions are performed by just the AIM control hub. So in this way, AiMX card can kill two birds with just one stone, efficiency and flexibility. So it can accelerate various LLM models with higher performance and low energy consumption. So as you can see, most currently known LLM all have similar architecture. In addition, the fully connected layer and multi-head attention layer shown in red account for the majority. So I believe our AiMX system can accelerate most LLM services. And here are the benefits of the AiMX for LLM service. AiMX can provide around 13 times performance than latest GPU system, and energy consumption is reduced to 17% of a GPU system. So in terms of inference latency, GPU-A system's processing time is around, as you see there, 6 seconds. But however, AiMX can provide around 200 terabyte per second of memory bandwidth for GenV function and can answer in less than 0.5 seconds. So if you have some real-time LLM application services, then it can be the best solution. And here, assuming that each AiMX card is equipped with just 16 AIM chips, it can provide 16 gigabyte of memory capacity and 8 terabyte per second of memory bandwidth. In terms of energy consumption, first, GPU is replaced with just a small AIM control hub. And GenV is processed by a dedicated MAC unit inside the AIM, so reducing energy consumption. And second, as the GenV computation is performed inside the AIM, so energy consumption for the off-chip data transmission can be eliminated. Last, as the GenV performance increases, so the processing time is shortened, and the static energy is also reduced accordingly. So in the end, the GenV operation is possible with only 17% energy consumption compared to the current GPU processing. So you can reduce huge amount of operating cost by using AIM system. And I think that for higher efficiency LLM service, I'd like to suggest that the combination of a GPU system and AiMX system. As introduced earlier, LLM service consists of the prompt stage, which is a computing intensive workload, and a response stage, which is an extremely memory intensive workload. So it is more efficient to process the prompt stage in a GPU system and process the response stage in our AiMX system. So in addition, usually ChatGPT type applications have a great portion of the response stage, but depending on the application, there are some kind of cases where the proportion of prompt stage is greater. So if the prompt stage system and response stage systems are configured separately, then you can configure the appropriate number of accelerator cards and servers according to your own application. So you can further increase that operating efficiency with that this kind of disaggregated system using AiMX card and GPU system. So actually, we developed that prototype of this kind of AiMX card introduced so far. So constructed that the AiMX reference system is like this, and ported that the LLM model and Q&A application on top of it. And as shown in the picture on the left, the AiMX card is equipped with that two AIM control hub chip with that FPGA and 16 AIM chips, providing 16 gigabyte of memory capacity per card. Also, as commented before, for higher hardware utilization, the AiMX reference system is composed of a GPU card for prompt stage and AiMX prototype card for the response stage. So actually, currently, the 13 billion OPT model and Q&A application are ported to this kind of system and showcased in a AI Hardware Summit and OSP Global Summit and SC23 in last year. And as you know, 16 gigabyte of memory capacity is not sufficient to run 13 billion LLM models, so we are using two AiMX cards in this showcase with some kind of parallelism. More importantly, each card is not limited to just 16 gigabyte. It's just a reference system. So, but additionally, AIM chip can be mounted to one card for larger memory capacity and higher performance. And so far, I have only focused on just the AI model processing itself. However, for actual AI services, you need to look at the entire AI service pipeline system. So, actually, you know that various services that combines big data and AI technologies are rapidly increasing. So in this slide, I'll briefly introduce that, just an example, graph driver service as an example to understand the entire data pipeline. So graph driver is that one of the widely used ride-sharing service, and it stores real-time data and analyzes it at the same time and sends a live report to the user in real time. And it also analyzes the kind of long-term stored data in order to give more information to the user and sends a weekly or monthly report. So through this kind of service, driver user can decide whether to grab a drive call in real time and predict his or her income or expenses in advance. In addition, by adding this kind of AI model to this data, so more personalized and localized service can be provided. Therefore, the basis of this service can be set to AI model and data analytics, this kind of two stage. So, as a general summary again, the entire data pipeline for AI service can be divided into kind of a data collection and data analytics and data use as shown in this kind of figure. So, among them, the third step to drive insight from the actual data is that the AI model. And the process of collecting data and analyzing that collected data and performing some kind of processing to pass them onto the AI model is collectively called just data analytics. Actually, from the next chapter, I will cover more various memory and computing fusion solution for data analytics and AI model other than just AIM solution. Actually, this is the last chapter. It's almost over. Actually, you know that nowadays hot keyword, one of the hot keyword is that CXL. So before introducing the next memory solution, I'd like to first explain the new interconnect, CXL. As everyone knows, then computer systems have developed from single core to multi-core and from homogeneous multi-core to heterogeneous computing. And heterogeneous computing system using CPU and GPU or various accelerators together are already widely deployed. And recently, this kind of a CXL, Compute Express Link interconnect, has emerged to support efficient connection between various heterogeneous accelerators, including GPUs and central CPU. Briefly, CXL can be viewed as an interconnect with a cache coherent and memory access protocol added to the current PCI interconnects that originally connected the CPU and accelerators. So CXL is composed of CXL.io, which is the basic protocol for PCI device support, and CXL.cache to support cache coherence, and CXL.mem protocol for memory access. The CXL.mem protocol was originally for the CPU to use the memory of the accelerator. By removing the accelerator and leaving just only the memory, then CXL can be used purely for the memory expansion. That we call CXL memory. So unlike that the existing DIMM memory, the memory connected by the CXL can be handshaked with the CPU. So it is possible to add various additional features such as that kind of DRAM cache or data processing core on CXL memory. So therefore, this kind of advent of the AI application introduced the previous slide, and the advent of this kind of CXL interconnect, there are more opportunities to apply combination of computing and memory solution to the actual system by using CXL. And now we introduce that CXL-based computing plus memory solution. And internally, we call it as just a CMS, computational memory solution, while we call die-level fusion as just AIM, accelerated memory. So as in the figure, it is the form of a memory card connected to the host by the CXL, and computing core is mounted as well. So when the host accesses the CXL memory, bandwidth provided by CXL can become a performance bottleneck. However, just by using those kind of computing core in the CXL card, then you can fully utilize that bandwidth that each memory device can provide. So the CXL bottleneck can be overcome and performance improvement can be obtained with that kind of a core. So in addition, by offloading this kind of memory intensive function to the computing core, then data movement between the server and CXL memory can be minimized to reduce energy consumption. And I'd like to talk about that, then which types of workloads are suitable for AIM, processing memory, or CMS, CXL-based computation memory solution, which have been introduced so far. So as shown in the picture on the left, AIM has just a small memory area that can be processed by that one processing element. It is memory bank size. So, but it has a large number of processing elements per memory capacity. Accordingly, it is very stable for a processing workload where the data to be processed is densely stored. So workload density is very high, then PIM is very stable for processing those kind of data. On the other hand, in the CMS, the memory area that one processing element handle is very large, and the number of P's per memory capacity is relatively small. So accordingly, CMS can well process workload with sparsely distributed data. So you need to decide which solution is best to use depending on just the workload density. And memory and computing solution, fusion solution is very much available in various forms other than the die-level AIM and card-level CMS introduced so far. For example, you can easily think of a storage level computational storage device, as shown in the figure below here. Although the basic concept is the same, but each characteristics and the problem to be solved are different each other. As explained in the previous slide, in the case of AiM, which is the die-level fusion, since a computing element operates for each banks in one memory device, the memory capacity per processing node is relatively small. In contrast, in the case of CMS, which is the card-level fusion, then since a computing element can use a number of memory devices, the memory capacity per processing node is relatively larger. Of course, in the case of a storage level, second level, third level, the memory capacity per processing nodes becomes larger. So as we already talked that, this kind of characteristics determine the appropriate workload to execute in each memory plus computing solutions. So we will have those kinds of various computing and memory fusion solutions. Actually, before closing this presentation, I'd like to introduce a new computer system architecture called data hierarchy. The basic concept is that every memory layer has its own processing unit to minimize data movement among entire memory hierarchy vertically. Since every hierarchy layer has not only memory but also processing element as well, so it is not just a memory hierarchy, but data hierarchy, we call it. Yes, concept is very simple, but there are lots of challenging questions to be solved to realize those kind of things. So today I'd like to introduce several interesting questions on this architecture. So first question is that then how to place the data at the proper memory layer? Because once we place the data, we don't like to move any kind of data between the layer. So provide the solution for this question, we need to understand the characteristics of the data and processing algorithm that use it. Second question will be, then what is the optimal process architecture for each layer? I think if we focus on specific applications, we can define it. For example, for AI system, then main memory layer process can be optimized to perform just a matrix multiplication, while storage layer processor need to optimize for kind of pre-processing operation like data analytics. And last thing, more complex question is then how to distribute the jobs between, to each data layers processor and how to aggregate that result. Actually, data hierarchy architecture is a kind of more complicated heterogeneous computing system. Not only horizontal workload distribution among heterogeneous computing unit, it also requires that vertical workload distribution and communication among the layers. So we should care both vertical and horizontal job distribution and communication simultaneously. I think this kind of data hierarchy concept is still just a buzzword yet, but I hope that someday we will have a chance to discuss it seriously together. So thank you for listening, and I hope my talk was interesting enough to keep your attention until the end of presentation. Thank you.
Okay, thank you, Dr. Lim. We actually have time for one or two questions. Anyone want to ask questions? Please, can you come over and use the microphone?
So my main question is about how do you compete with GPUs? So GPUs have 128 or stream processors and so on. And how many processors do you have within your AIM solution next to 1 gigabyte? How does that compare? As you scale memory, does the compute similarly scale with HBM plus GPU together?
Oh, actually, we are just focusing on that GPU cannot do. Actually, there are two kinds of functions in LLM. One is just a gem. Gem function is matrix by matrix multiplication, which is GPU can do well. In that case, the performance depends on that processing performance itself. So GPU can do well with a very massive parallelism. But GemV is that matrix by vector multiplication, which is that most memory intensive workload. So the performance does not depends on that the processing performance. Yeah, that's why we focus on those kinds of things with that just minimum performance unit in the memory banks. Thank you.
All right, next question.
Thank you for that interesting talk. I have a question about the picture of the data hierarchy. I like this picture, but the picture is very complicated. So my question is, how can we program it? How can we use that complicated system? Is there any good abstraction?
Actually, it's that question that I want to ask you all in this community. So actually, that's why in a modern computing system, the most as consumption is that just moving the data. So we need to minimize that moving data. Then how can we do that? How can we place that proper position in that memory hierarchy or something like that? And how can we communicate with each other's processor in a vertically and horizontally? So that's why I ask the question to this kind of software community to solve this kind of problem together. Yeah, that's it.
Thank you for the nice challenge.
Perhaps the good starting point is SK hynix sponsoring next year's ISMM or PLDI. So that we can find answer together. Okay, any other questions? I think we are about time. So let's thank the keynote speaker again.